In this video, we are going to learn about viscosity, Newton's law of viscosity, what is dynamic viscosity and what is kinematic viscosity. We will see the differences and their units in SI and CGS system of units. So before we start, let me ask you a few questions about this experiment. So as you can see, there are four different fluids: honey, maple syrup, corn syrup, and this soap. So they were simultaneously dropped from the same height, and we can see easily that maple syrup is the liquid which will first reach at the bottom. While other fluids are taking much time, maple syrup completes this journey in 1.33 seconds. It takes just 1.33 seconds for maple syrup to complete the same journey for which the other fluids like honey and corn syrup, they are not able to reach at least till the middle of that height. So why is that? So that different fluids are having different speeds. What is the reason behind that? So this is a fluid property that we are going to study. Now the viscosity is a property that represents the internal resistance of a fluid to motion or fluidity. So this is basically same as that of friction in solid. Remember, it can be compared to, it is not actually, but compared to friction. Remember this. Why? Because anything which flows. So now suppose we have two layers of fluid. They are trying to flow in this direction. So this will come in between these layers. It will act in between these layers, and what it will do? It will try to resist them from motion. So that will, the direction will depend on the velocity, that which layer is flowing with which velocity. But as of now, we are interested in this internal resistance of a fluid to motion or fluidity. So remember, this internal resistance is important term. It will appear in between the layers of fluid. So these are basically the layers. These are the layers, this and this. So for any two layers, this internal resistance will come into the picture only when the fluid is in motion. Remember this, when the fluid is in motion. Now why does it happens? So the reason is different for liquid and gases, but it will be present in both. When we talk about viscosity, it is a phenomena that develops in a fluid, but in liquid it is due to cohesive forces. Now what are the cohesive forces? Cohesive forces are actually the force of attraction between the molecules of same matter. Now what is this molecular momentum transfer in gases? So remember, gases molecules are at a distance. We have already seen the structure of gases. We are talking about gases. So in gases, molecules are actually very far. They are not closely packed as that of in the case of liquid. So here what will happen? These molecules are having some mass and velocity, and they are moving randomly. So whenever one molecule collides with the other molecule, so what happens? It transfers energy. That energy it transferred, and it loses itself energy. So it will, the molecule, when it will get collided with the other molecule, so it will transfer some energy, but it will lost its own energy. So that is the reason that the resistance comes into the picture due to molecular momentum transfer. We know that momentum is defined as, how momentum is defined? Momentum is defined as mass into velocity. So these molecules are moving with some very high velocity. So that means this is dominating. Now see, in cohesive forces. If we talk about cohesive forces, so in gases, the cohesive forces are less. If we talk about cohesive force in gas, so this is actually less than cohesive force in liquids. So remember, in liquids also there will be molecular momentum transfer, but the value will be very less. In gases there will be cohesive forces, but the value will be less. So this is important from objective point of view, that you should remember the difference, how viscosity appears in liquids and how viscosity appears in gases. Now, moving on to the Newton's law of viscosity. So there are certain assumptions we should keep in mind. So this law, while driving this, we will observe two parallel plates with a gap L between them. Shear force F is applied on upper plate, which moves with a velocity v. Space between plate is filled with a viscous fluid. V and L are not very large. That means the velocity and the length between the parallel plates, they are not very large, and A is area of contact of the fluid with the upper plate. So these are certain assumptions. Now we can see the diagram here. If you see in this diagram, so this is top plate, this is bottom plate. So there are these two plates. Now if you observe any liquid particle, so one liquid particle here, and we are observing it with respect to this bottom plate. So with respect to time, what will happen in this dt time? What will happen? This particle covers a distance up to this point. So what is dA? dA is equals to displacement. dA is equals to displacement of fluid particle at n in dt time. So remember this. So this is what going to happen. This is changing by an angle d theta, right? So can you write the strain produced here? Can you write the strain produced here? Yes, obviously we can write the strain will be d theta. The strain will be d theta. So we will compare it with this. Now suppose we take two layers here for our discussion. Now what are these two layers? These two layers are such that now here the velocity of particle is 0. Why? Because this plate is at rest, this plate is at rest. So if this plate is at rest, the velocity of fluid particle will be 0. This plate is, top plate is moving with velocity v, so velocity of this particle will be v. But we are interested in any two different layers at which we have to determine the velocity. So now let us take these two are the layers for which this layer is moving with velocity u and this layer is moving with velocity u plus du. This layer is moving with velocity u plus du. Now we are interested in this. Now look at this. This triangle is important. This triangle is important for us. Remember this triangle, because this will be the same angle. Which angle? D theta, which we have seen. Remember? So how to get the value of this d theta? So we should know that this d theta can be determined by knowing the difference. Which difference? Now here this is y-axis and the total distance will be, here this is y-axis and this gap we can take as dy and that too at a height y. So the same thing we will take up here, that from this base, this height is y, and after this y height, we have this thickness as dy. So we will take it up like this. Now in dt, in dt time, what will happen? Now suppose if there would have been any fluid particle, then how much it would have moved. So now pay attention here. In u times, in with u velocity and dt times, what will be the displacement of fluid particle at this? So you will simply write, sir, this is u into dt. This is the displacement of fluid particle. But at the same time, what is the displacement of fluid particle at this point? So you will say, sir, this is a little longer. Why? Because you will say, sir, this is u plus du multiplied by dt. This is the displacement of fluid particle. Fine, no problem with that. So in that case, now we have to look for this difference, because this is u dt and this is the same length. Now this must also be the same. Well, how much u dt? How we can see that this length is same? Now we just need to break it up a bit. This term can actually be written as u dt plus du into dt. Remember this. This is the first step and this is the second step. Now we will try to club them. How we can club them? So we can club them in this manner, that this u dt part is nothing but this part. Same, u dt, u dt. And this du dt part is what part? This du dt part is this part. So let me focus you, let me tell you to focus on this particular triangle. Why this triangle? Because here you will come to know about that this angle is how much? This angle is actually d theta. Remember, so how this d theta value can be written? How this d theta value can be written? That is important part for us now. So that d theta value can be written as tan d theta equals to, now it must be height, this difference, upon base. So base is nothing but dy. But what is this height? So this height is this total length minus udt. So height is nothing but this part, or in other words we can write it in this manner, that u dt plus du dt minus u dt, this divide by dy. It can be written like this. Now if you see, this du dt and this du dt, they will get cancelled out, and for very small value of theta, if angle is very small, then we can approximate this tan theta is to be d theta, which can be written equals to, d theta equals to du dt over dy. So remember this expression, which we can simplify further, and we can write as, that d theta over dt, which is equals to du over dy. Now this is again very important relation for us. Why this is important relation? Because it tells it about, now look at this part. This part is actually known as shear strain rate. This part is shear strain rate, while this part is velocity gradient. Remember, both are equal. Now, coming back to this Newton's law of viscosity. So, as per Newton's law, what he said, Newton's law, he said that tau, the value of shear stress, is directly proportional to this d theta by dt, or tau is directly proportional to, now this d theta by dt we can replace with du over dy. So remember this, if you remove this proportionality, so you have to introduce a constant. You have to introduce a constant, and that constant, this is Newton's law, that constant is actually viscosity. So if we remove this, we will be left with this equation, that tau is equals to mu du over dy. Remember this, this is the expression which will be used in many times, that this is the expression for shear stress, and this mu is actually known as dynamic viscosity. So let me write it for you once again. Tau is actually mu du over dy. So in this equation, this is Newton's equation for viscosity, and this mu value is actually known as the dynamic viscosity. Now if you see that it is defined as shear stress required to produce unit velocity gradient. So we can write it in this manner, that mu is equals to this tau required to produce du over dy. This is in accordance with our definition. It is known as dynamic viscosity because its definition is in terms of forces. Shear stress directly relates with shear forces. Now we look at on the units of dynamic viscosity. Now we directly look at its unit. The units of dynamic viscosity can be given in SI units and in CGS units. So how we can give the unit for this viscosity? Let me write it for you. So this can be written as, now look at this, tau value is Newton per meter square. This is tau value, right? Now multiply by, this can be written as dy upon du. So dy value is again in meter, and du value can be written as meter per second. So in that case, what we are left with, this is meter and meter will get cancelled out. This second will go up. So the unit in SI unit will be, this is basically SI unit. So we can write it as, this is Newton second per meter square. So this is SI unit, right? This is SI unit. But there is one more way to write a equation like this, because why? This Newton per meter square we already know as Pascal, and second is also there. So Pascal seconds can also be written. Pascal seconds can also be written its unit. This is also very important. So this Newton second per meter square and Pascal second you should keep in mind. And what else we should know? We should know its CGS unit also. What will be the CGS unit for viscosity, right? So let me write it, because CGS unit is also very important from exam point of view. So CGS unit can be given as, so in CGS how we can represent the tau value? Force, that is dyne per centimeter square, multiply by centimeter divided by centimeter per second. So in that case, like if you go with this, you will be getting again this centimeter and centimeter will be cancelled out. So you can have it as dyne second per centimeter square. Dyne second per centimeter square, and this value is also known as poise, POISE. This is important from exam point of view. Remember this, CGS unit is also important, poise. You should keep this in mind. Now, what is the conversion of this poise with Pascal second? So we should know that 1 Pascal second, always remember this, 1 Pascal second, 1 Pascal second is equals to 10 poise. Remember this, 1 Pascal second is equals to 10 poise. So you should also keep this in mind. Very important unit. This we should remember. This we should remember. Now, moving on to kinematic viscosity. What is kinematic viscosity? In fluid mechanics, heat and transfer. This fluid mechanics and heat transfer, they are two important subjects. The ratio of dynamic viscosity to density appears frequently. That's why we have decided its name, that is known as kinematic viscosity. It is defined as the ability to diffuse the disturbance in molecular momentum. So basically what we can write, that kinematic viscosity, the symbol will be nu. So the nu value is nothing but the dynamic viscosity upon density. So remember this, this is the kinematic viscosity. Now, what is the unit for this kinematic viscosity? What we can write as the unit of kinematic viscosity. So remember that for this kinematic viscosity, now we just need to write the value of mu. Now what is the unit of mu? So mu unit is in SI unit, obviously first. The mu unit was Newton second per meter square. But the density value is mass per unit volume. So density can be written as, this density can be written as mass, that is kg per meter cube. Remember, like this. So here you can see that this meter square can get cancelled with this meter cube. So we will be left with meter. That can go up, right? Now this Newton value, how this Newton we can change? How this Newton we can change? So this Newton we can change, again Newton is force. Force can be expressed as mass into acceleration. So we will write it like force, Newton can be written as mass into acceleration, kg, acceleration meter per second square, again second is there, and here again divide by kg, and here again meter. So as you can see, again if you simplify it, so what will happen, kg will get cancelled out, this second will cancelled out. So we will be left with meter square per second. Remember, this will be the unit of kinematic viscosity, meter square by second. And obviously this unit is SI unit. Now in CGS unit, this will be in CGS unit, this will be, obviously instead of meter, what you will write, new unit will be, instead of meter, centimeter square per second. So obviously this is going to be the unit for kinematic viscosity in CGS. This is also known as This is also known as, what is the name? Stoke, right? And for the conversion, you should know that 1 Stoke is equals to 10 to the power minus 4 meter square per second. So this is also needs to be remembered. This value we need to be remembered for kinematic viscosity. Now we will see the effect of temperature on viscosity. So the effect of temperature on viscosity can be understood by, now suppose the temperature, if you increase the temperature, then what will be the effect on dynamic viscosity? Now try to understand this in this manner, that dynamic viscosity of liquid will get decrease, while the dynamic viscosity for gases will gets increase. Why is that so? Because in liquid the viscosity is due to cohesive forces. Once you heat it up, you increase the temperature, then cohesive forces are going to be decreased, because molecules will get more energy and they will be separated. So cohesive forces will become weaker, and that's why in liquid viscosity, dynamic viscosity will decrease. But in gas, what will happen? The molecular momentum transfer will get increased as the temperature of the gas is increased. Now, in case of kinematic viscosity, again for the liquid, this viscosity will decrease. For the liquid, this viscosity will decrease, but for the gases, this velocity is again going to increase, right? So effect are same on dynamic or kinematic viscosity. So it is easy to remember for us. Now we will see the effect of pressure. Suppose you want to see the effect of pressure. So effect of pressure is basically, we can say that effect of pressure is practically independent. Practically independent. Why? Practically independent except for very high increase in pressure. We'll write it, except for very high increase, very high increase in pressure. So this we should remember, but we will see the effect of pressure. So that can be given as, now if we talk about pressure, so if suppose we increase the pressure, then what will happen? If we increase the pressure, then when we talk about dynamic viscosity, there will be no change, either liquid or gas, no change. Kinematic viscosity, again liquid, no change. But the gas, if you consider, so the gas kinematic viscosity will decrease. Why is that so? Because kinematic viscosity is equals to dynamic viscosity upon density. So the moment you increase pressure, the density will increase. So increase in density will overall reduce the kinematic viscosity. So only this thing is important from your exam point of view, because only this will change. The kinematic viscosity for gas, only this will change. So that's it for now. Thank you.